Okay, let's talk about the Markov chain, but with matrix representation. It's a very powerful tool. We can represent Markov chain as a matrix by just representing all the state from going to state I to state J as every element in the matrix. Recall for a steady state, we have probability at staying at state I as pi I. Based on this formula, we can have a matrix form like that. If we do a transpose on both sides, we will have this. We'll have this expression. This essentially, if you remember, in linear algebra, this is essentially equation to solve eigenvalue and eigenvector. So this equation essentially is solving a eigenvector with the eigenvalue of 1. It makes sense in the sense that no matter how many times you multiply this eigenvalue, it will not decay nor explode. It will stay at the steady state. So let's look at an example. Just with a random transformation matrix P, a transition matrix P, and we just plug into the normal way to solve an eigenvector. So the matrix is P transpose. P transpose multiply so minus lambda I, where lambda is 1. So you got this, and do a row reduction. You ended up just pretty much add this second row to the first one. You have this. This is I, this is F. Then you got your null space. You can review the linear algebra. I put the link down the description. Then we have this, which is pretty much pi transpose, but we need to normalize this since we need the probability sum together should equal to 1. Thus we end up having this steady state 4/7, 3/7. For the Markov chain that has absorbing state, then we can represent the matrix into like 4 blocks essentially. One block is a transient state, so pretty much if you have a absorbing state, transient state is likely just like here among themselves, and this one is the absorbing state, for instance. So this is pretty much Q, a transient state. R is the transient state to the final state, which is this. I is pretty much absorbing state, if that makes sense. We'll discuss further in the concrete example. So recall the expected steps to absorption state as mu I. The expression is written as such. Again, the more lengthy discussion is on the description. So we know that if we go from already absorbing state, it takes 0 steps to get there. So if we multiply the P to mu, essentially we're multiplying to a block. We can multiply by a block, and then ended up it become it become I mu, since the very bottom does not matter to us. We just kept the transient state calculation. So we only left the one that is the mu as one that the vector that only in the transient state, not the absorbing states. We have this equation in the vector form, and actually tensor form, and we multiply. We put this on the left side and multiply the invert in both sides, and then we ended up having the step it takes equals ni, where n is a fundamental matrix I minus q inverse. Similar to the steady state absorbing steps, in the absorbing steps, the probability of the absorbing from the state I to state j, bij, so going from state I to the final absorbing state, we're going to call a pretty much a hybrid almost of this, this and this. This can be divided into the going directly from I to j, which is the transient to the absorbing, and the probability of going from I state to Q state, and then from K, and then go from K to J. Translate this to a matrix format, you will end up getting Rn, where R is this block of matrix. Let's look back to the question we done before. How many, like we'll roll the die until we roll the die 6 back to back. So it can be described as this Markov chain essentially. 0, and you can keep going 0. The number is number of consecutive 6s. So 0, you can always roll other numbers, which is 5, 6 probability, and then 1, 6 probability to go further, and 1, 5, 6 to go back, and then 1, 6 to go to second, and then absorbing at the second one, because we only need 2 consecutive, which is back to back. So writing this Markov chain to a matrix, it will look like this. So 0, 0, 1, 0, and 0, 1, 1, 1, and 1, 2, and then finally 2, 2, which is absorbing state, is 1. Thus we have the Q, R, and I. We're going to calculate first. We almost always calculate the fundamental matrix, I minus Q, and then we need to do the inverse of this, which is, you can review the linear algebra. So pretty much you do a row reduction with the side of the identity, and then you keep doing it until you get on the left matrix identity, and right will be the inverse. So I ended up getting fundamental matrix like such, multiply by vector I. So by vector I forgot to mention, vector I is pretty much a vector of ones. So just pretty much 1, 1, 1, 1, 1. So you just pretty much 36 plus 6, 42, and 30 plus 6, 36. So this pretty much means it takes 42 rows to go from the beginning to 6 back to back. And it will take 36 rows to go from when you already got 1, 6. But because there always is not taking 6 time because you will have some probability to go back to zero state. And the probability of absorption from other different states are here multiplied by n, matrix multiplication 1 1. So both have 100% chance to be absorbed into the final state of 2 because there's only one absorbing state, which makes sense. It should be 100% both being absorbed into the final state. As you can see, it is very powerful tool. This opens the door in the sense that as long as we can describe in a matrix form, sometimes even a sparse matrix, we can use a computer to calculate all the desirable features that we want.